Pluto is a far-off and secretive yet more honest planet that was once a part of our nearby planetary framework. However, recent shocking declarations by leading astrophysicists Neil deGrasse Tyson and Michio Kaku have brought Pluto back into the spotlight. They suggested that this frigid world is on a potential collision course with Neptune. But how could this actually happen? And what might be the consequences of such a colossal event? Are we witnessing a perplexing cosmic anomaly? Or is there something more to this impending catastrophe? Join us as we examine the potential outcomes of a Pluto-Neptune collision. Pluto, a former planet that was reclassified as a dwarf planet, remains a subject of interest and study in the vast universe. According to recent predictions by leading experts, Pluto's orbit is dangerously close to Neptune's. Astrophysicists Neil deGrasse Tyson and Michio Kaku are both raising the alarm about a potential catastrophic collision between these two celestial bodies, which could pose a massive risk to Earth. But how is such an event even possible? Pluto's journey around the Sun is unlike that of any other planet in our solar system. It takes a staggering 248 years to complete a single orbit. Since its discovery in 1930, it hasn't even finished one full revolution. However, the intrigue doesn't stop there. Pluto's orbit is marked by its highly elliptical shape, deviating significantly from the nearly circular orbits of the major planets. What makes Pluto's orbit even more astonishing is its inclination, tilted 17 degrees to the ecliptic plane. Pluto's orbital path is far more erratic compared to other planets. This tilt and eccentricity add layers of complexity to its orbital arrangement. Perhaps one of the most fascinating aspects of Pluto's orbit is its intersection with Neptune's. For about 20 years in each orbit, Pluto actually moves closer to the Sun than Neptune, defying what we might expect from their positions in the planetary system. This raises the obvious question: why hasn't Pluto collided with Neptune? The answer lies in the gravitational influences of other planets. The study of Pluto's orbit began soon after its discovery. Initially, astronomers tried to understand its peculiar trajectory. Unlike other planets whose orbits lie relatively close to the ecliptic plane, Pluto's orbit stands out with its steep inclination and irregular shape. The mystery deepened when astronomers realized that Pluto's orbit does, in fact, cross Neptune's. Despite these complexities, Pluto's orbital stability is evidence of the intricate dynamics of celestial mechanics. The three-body problem in space. How three objects such as Pluto, Neptune, and the Sun interact gravitationally is incredibly complex. It's like predicting where they will go based on where they started and how they pull on one another. In Pluto's case, this problem highlights how its orbit, Neptune's orbit, and the Sun's gravity all interact in a delicate balance. Several key concepts explain why Pluto and Neptune do not collide. 1. Non-simultaneous libration. This means that when Pluto crosses Neptune's orbit, it is positioned about 90 degrees away from Neptune. This spatial separation prevents their paths from intersecting. 2. Orbital precession. This refers to the gradual shift in the orientation of an orbit. For Pluto, this means that when it gets closest to Neptune or any other giant planet, it is positioned far above or below their orbital plane, adding an extra layer of protection against potential collisions. 3. VZK wobbling. Named after three scientists, this phenomenon explains how celestial bodies influence each other's movements through gravitational interactions. In Pluto's case, VZK wobbling helps stabilize its orbit over long periods, despite its chaotic appearance. Although Pluto's orbit may seem unpredictable, these gravitational forces ensure that it moves smoothly over extended timescales. The VZK wobbling demonstrates that, despite the apparent chaos in space, patterns and laws maintain some level of order. These mechanisms help keep Pluto's orbit stable, preventing it from colliding with Neptune or straying off course. The three-body problem is crucial for understanding how orbits evolve due to gravitational interactions. Studying this helps us learn more about Pluto, our solar system, and even distant worlds and their stars. Numerical simulations in the late 1980s revealed that, despite its stabilizing properties, Pluto's orbit is technically chaotic, with minor deviations in initial conditions leading to significant differences over centuries. However, these orbital peculiarities have been found to maintain stability over extremely long timescales. By analyzing more recent automated calculations, scientists have gained deeper insights into how giant planets like Neptune, Jupiter, and Saturn influence Pluto's orbit around the Sun. Neptune has a unique relationship with Pluto. For every 2 orbits Pluto completes around the Sun, Neptune completes 3. This resonance helps maintain Pluto's orbital stability. However, Neptune isn't the only factor at play. Jupiter's immense gravity also plays a crucial role in keeping Pluto's orbit steady. Saturn, too, contributes to this stability. These studies indicate that Jupiter's massive gravitational influence is strong enough to ensure Pluto remains on a consistent path for a long time, possibly even millions of years. So, perhaps Neptune, Jupiter, and Saturn are working together to keep Pluto safely traveling through space without encountering major disruptions. These orbital eccentricities are essential for maintaining order in the solar system. Without these stabilizing mechanisms, our solar system would be a much more chaotic place. Bodies like Pluto could collide with others or be ejected from their stable orbits, triggering a chain reaction affecting other celestial bodies. For Pluto, especially with discussions about its potential collision with Neptune in the future, understanding its orbit is crucial. This provides a clearer picture of the dynamic nature of our solar system and the cosmic forces that govern it. Close by planetary framework, the instance of Pluto shows how even the most apparently unsound orbits can reach a state of equilibrium through the complex interaction of gravitational forces and orbital mechanics. It also highlights the importance of continuous observation and study of these phenomena to better understand our place in the universe. Exploring the depths of space often forces us to confront the strange nature of celestial bodies. Pluto's orbit is a prime example of this inconsistency. The concept of orbital chaos, which refers to the delicate dependence of a celestial body's orbit on its initial conditions, is clearly demonstrated in Pluto's case. This means that even slight changes in the dwarf planet's position or velocity can drastically alter its long-term orbit. Using digital simulations has been immensely helpful for scientists in understanding how Pluto moves in space. These simulations use complex mathematics to model how Pluto and other celestial objects, like Neptune, exert gravitational influence on each other. By tweaking small details in the simulations, space researchers can observe how even minor changes can result in significant differences in Pluto's eventual location. In the late 1980s, these simulations revealed something fascinating about Pluto's orbit. Despite having features such as eccentric libration and orbital precession to maintain stability, its orbit can still be unpredictable and erratic. If one starts with even a small variation in Pluto's position or velocity, its orbit could look entirely different after just a few years. Yet, despite this apparent chaos, Pluto's orbit remains stable over immense timescales, spanning billions of years. This suggests that Pluto's journey around the Sun follows a certain order, even though it appears erratic at first. Predicting celestial movements, especially those involving irregular orbits like Pluto's, is a major challenge. The inherent unpredictability of these systems means that long-term forecasts are often riddled with uncertainties. While mathematical models provide excellent tools for understanding and predicting the future movements of celestial bodies, they also highlight the limitations of our predictive abilities. These models heavily rely on the accuracy of initial conditions, and even the smallest error or distortion can lead to vastly different outcomes, making precise predictions a daunting task. Beyond the chaotic nature of planetary orbits, Pluto reminds us of the ever-changing and dynamic nature of the universe. While we have made significant progress in understanding space, Pluto's case serves as a reminder of how much remains unknown. Understanding the gravitational effects of giant planets on Pluto's orbit provides valuable insights into the broader dynamics of the solar system. It demonstrates how the presence and positioning of each planet can significantly impact the stability and trajectory of other celestial bodies within the system. So why have leading astrophysicists recently raised concerns about a possible collision between Pluto and Neptune? Despite the intricate forces working to prevent such an event, Neil deGrasse Tyson, a prominent astrophysicist and influential figure in modern cosmology, offers a unique perspective on the mysteries of our solar system, particularly the intriguing case of Pluto. Tyson, known for his role in reclassifying Pluto from a planet to a dwarf planet, provides insightful analysis on the evolving understanding of celestial mechanics and the public's fascination with the lesser-explored regions of space. His stance on Pluto's reclassification is based on the ever-expanding knowledge of our solar system. He views the change not as a demotion but as a necessary adjustment to our growing understanding of the diverse bodies orbiting our Sun. Tyson's approach to celestial mechanics is one of continuous learning and adaptation. He sees the complexities of orbits like Pluto's as a testament to how much there is still to discover in space. These lingering questions keep space exploration so compelling. However, despite Tyson's optimism, his thoughts on Pluto's potential collision with Neptune suggest that we may still have many mysteries to unravel. Will Pluto collide with Neptune? Or is this just another moment of chaos in the ever-changing cosmos? Only time and further research will tell. For now, we are left with a deeper curiosity about how little we truly understand about our own solar system. We continue studying these celestial phenomena with the goal of uncovering more of the secrets that lie beyond. The possibility of a Pluto-Neptune collision raises yet another question about the enigmatic and captivating universe we inhabit. The potential for such an event challenges our conventional understanding of planetary stability. The idea that two celestial bodies with vastly different characteristics could collide is both unsettling and fascinating, especially considering the current relative stability of their orbits. Given that Pluto is located in the outer reaches of the solar system, far from the major planets, and Neptune is a massive gas giant with a strong gravitational field, the implications of such a collision would be profound. It would reshape our understanding of gravitational interactions and the evolution of the solar system. To grasp the dynamics of a potential collision, one must first consider the structure and properties of both planets. Pluto, despite being a dwarf planet, contains various elements and compounds believed to exist in a frozen state due to the extreme cold of the outer solar system. Its surface is covered in nitrogen ice, and it has an atmosphere composed primarily of nitrogen, methane, and carbon monoxide. In contrast, Neptune, a giant gas planet, is composed mainly of hydrogen, helium, and other lighter elements, with a deep and dense atmosphere. A collision between such vastly different bodies would dramatically alter their structure and behavior, potentially creating an event visible across immense cosmic distances. What makes this hypothetical impact particularly intriguing is the influence of other planets and celestial bodies within the solar system. While Neptune's gravity plays a dominant role in maintaining Pluto's orbit, it is not the only factor at play. The presence of Jupiter, the largest planet in the solar system, is another crucial element. Jupiter's immense mass, strong gravitational field, and stabilizing influence on Pluto's orbit prevent it from drifting too far into Neptune's domain. Additionally, Saturn's gravitational pull further complicates the dynamics of the outer solar system, making a catastrophic event between Pluto and Neptune unlikely. However, despite the apparent risks, ongoing research has also shown that the relationship between Pluto and Neptune is not as straightforward as a direct collision course. The gravitational resonance between the two planets, where for every 2 orbits Pluto completes around the Sun, Neptune completes 3, creates a type of celestial lock that prevents them from coming into direct contact. This resonance is a crucial reason why Pluto and Neptune's orbits, while crossing in the vast expanse of space, have never resulted in a collision.